Let's now start to consider what's happening throughout the flight, not just what's happening initially. And so we'll first start with acceleration. We've already mentioned how in the horizontal direction there is no acceleration. So x, now we're talking about acceleration, so x double dot is equal to 0. The only acceleration that we are interested in is in the y direction, and that is the acceleration due to gravity. Now, because we conventionally say that up is positive, then down must be negative. And using g, lowercase g, to represent gravity. So in terms of an actual vector for acceleration that takes into account both the x and y components, we can say that the acceleration vector, which we'll call a, and it's got its little tilde, so we know it's a vector, is 0 lots of I minus g lots of j. And so obviously this can be simplified to be minus g times the unit vector j. And so this is the acceleration vector of a projectile throughout the entire flight. Let's now use this to work our way towards an expression for the velocity vector of a projectile at any point during its motion. Since acceleration is the derivative with respect to time of velocity, then going the other way means that we can integrate acceleration to come up with velocity. So we're going to integrate the acceleration vector with respect to time. And since acceleration is just a constant, this negative g, in the j direction, okay, but it's just a constant, that means when we integrate with respect to t, remember, we're going to get minus gt, and it's still in the vertical component, plus we have some constant. In this context, we need to consider it with vector notation. But just like we've done before with integration, when we're talking about an indefinite integral, as we are here, we want to work out what this constant is. And so let's think about the initial conditions for velocity. When t equals 0, the velocity vector, okay, this is what we just did, is equal to the initial speed v times cos theta, and that's in the horizontal direction, plus v sine theta in the vertical direction. So if we substitute those values back in here, remember this was velocity, we can say, all right, v cos theta I plus v sine theta j is equal to minus g times t, but what is t? It's 0, okay, plus our constant. And so since this clearly goes to 0, our constant must be this initial vector expression. And so our overall vector at any point during the motion is minus gt j plus v cos theta in the I direction plus v sine theta in the j direction. And we know that with vectors we can collect the like terms. So horizontally we just have v cos theta I, and remember this should match up with what we talked about. The horizontal velocity of a projectile remains constant throughout the entire flight. So this v cos theta won't change. However, it is the vertical component that does change. And so we have this minus gt part plus the initial vertical velocity. And so this is the expression for the velocity of a vector, the velocity vector of a projectile, at any point during the flight. Now this process that we have just gone through to come up with the velocity vector, this is something that you need to become familiar with yourself. We can't just purely remember these. Unless a question specifically gives us this, we're expected to derive this ourselves. So starting with the fact that acceleration is minus g times the j vector, and integrating, we need to be able to come up with this. So it's a good idea if you become familiar with what we've just done. Just spending a bit more time now analysing this equation and matching up the algebra with what we already know to be true. This horizontal component here does not have t in it, right? The horizontal component is independent of t. Okay, so that just further confirms that at no point in time will this change. However, the vertical component does involve t. And so therefore, at some point in time, this vertical component for velocity will become 0. And that is the maximum height that the projectile reaches. It's like a turning point, right? And we can picture that graphically. In the next video, we'll do our first projectile motion example.